Welcome, everyone. We're going to start Chapter 11, which is Oxidation and Reduction. We'll start this by a quick demonstration of oxidation and reduction using zinc, an iodine tincture, and some bleach. For this demo, I'm going to attempt to add a little bit of reduce tincture of iodine with some zinc. There's iodine tincture. Now, it says to use like galvanized nails or galvanized tacks. Rather than that, I'm going to try to use powdered zinc. Let that go. See how well it goes. I might have to add more. We'll see how it goes. Now it's just a matter of waiting. After multiple additions of zinc, see how the solution is essentially colorless. I'm going to pour this off, react it with bleach. Colorless. Now what should happen if I add bleach to this? Adding bleach. Oh. And it has resumed its original brown color. I'm sure adding more bleach would further oxidize this. See, now I don't think I need to add any vinegar. Doesn't appear to be very lumpy. So, the process we've just seen is that the zinc was oxidized to zinc 2+, as the iodine I2 is reduced to I-, which is a colorless liquid. Upon adding sodium hypochlorite to the solution, the sodium hypochlorite is reduced to sodium chloride, while the iodide is oxidized back to just iodine. This reaction was caused by electron transfer. We'll talk more about how and why a little bit later, but first let's look at batteries. Now, batteries are probably the most common application of all the types in our redox reaction, our oxidation reduction reactions. That we can have lead acid car batteries, we can have nickel cadmium batteries in our tools. Probably the most common one we've heard of is alkaline batteries, which are AAAs or AA batteries. Now there's some dry zinc cells that were replaced by alkaline batteries that I have a cross-sectional picture of, that not as commonly used nowadays, but they're still there. We have lithium ion batteries, which are in our computers and in our Tesla vehicles. So now the zinc carbon dry cell is the book starts by talking about this. We won't talk about that as much, but it's a version of the Leclanche cell. It's not the best cell. It uses zinc and magnesium oxide and ammonium chloride electrolyte, and it goes the zinc turns to zinc chloride, and the manganese dioxide forms the essentially manganese 4 oxide turns to manganese 3 oxide, and we form ammonium hydroxide. Now this works reasonably well. However, the ammonium chloride will eventually dissolve its way out of the container and will react with the zinc. And so these guys actually have a very short shelf life. So the more common version is the alkaline earth battery with alkaline batteries or alkaline batteries. Same generalized reaction, except instead of ammonium chloride, we use potassium hydroxide, which is why they're called alkaline. Alkaline is one of the common words for base. Now, the zinc Instead of going to zinc chloride, goes to zinc oxide. But the manganese does the same general process, goes from Mn4 plus to Mn3 plus. And these have a much longer shelf life, though when they explode, they do form crystalline potassium hydroxide on the surface. So not super safe when they explode, but they last a lot longer. For a battery to work, it must complete a circuit. And the circuit is simply the path the electrons have to follow. The idea is that you have some sort of equipment, and the battery touches the head and the end of it in the path so that when the button is pressed to turn it on, it completes the circuit and it draws electricity. The electrons are allowed to flow and power the equipment, whether it's a flashlight or your calculator or anything. We have a simple battery that's completing the circuit. Now, the circuit is powered by the electric current, which is simply the flow of electrons. As the zinc is oxidized to zinc oxide, we're releasing 2 electrons that can flow through. The actual reaction is zinc plus hydroxide, 2 hydroxide goes to zinc oxide and water. But the zinc will lose electrons, which will flow through the metal casing, complete the circuit, power the light bulb, power the battery, and then go through and reach the bottom of the battery and flow into the manganese and change it to Mn4 plus to Mn3 plus. So doing MnO2 plus water forms Mn2O3 and hydroxide. And the reaction is such that the hydroxides and the water cancel out, and so the reaction looks a lot simpler. You have some sort of equipment, and the battery touches the head and the end of it in the path so that when the button is pressed to turn it on, it completes the circuit and it draws electricity. The electrons are allowed to flow and power the equipment, whether it's a flashlight or your calculator or anything. We have a simple battery that's completing the circuit. Now, the circuit is powered by the electric current, which is simply the flow of electrons. As the zinc is oxidized to zinc oxide, we're releasing 2 electrons that can flow through. The actual reaction is zinc plus hydroxide, 2 hydroxide goes to zinc oxide and water. But the zinc will lose electrons, which will flow through the metal casing, complete the circuit, power the light bulb, power the battery, and then go through and reach the bottom of the battery and flow into the manganese and change it to Mn4 plus to Mn3 plus. So doing MnO2 plus water forms Mn2O3 and hydroxide. And the reaction is such that the hydroxides and the water cancel out, and so the reaction looks a lot simpler. Now, these oxidation reduction reactions don't just occur in batteries. You can run a clock off of these. The clock, all you need is copper and zinc plates, 2 wires, and some sort of vegetable or fruit. Most common one is a potato. You hook the 2 wires into the potato and you can run it through and power a clock. But you could do this with an apple. You could do this with a lemon or lime, any sort of citrus fruit. You don't even need some sort of plant product. You could use wet soil. You could run a soft drink. You could even just use salt water. The whole idea is you just need some sort of a liquid medium to pass the electrons to complete the circuit through. You just need the electrolyte to complete the circuit. The metals are actually the most important part, whether you have to use the copper and the zinc to make this work. When you put these metals and the electrolyte, we are completing an electrochemical cell, which is just a cell or battery that produces electricity from chemical reactions. One of the most common types comes in 1836 with John Frederick Daniell. He's the first professor of chemistry in London's King College. So his electrochemical cell is he placed two beakers, one with a zinc plate and zinc sulfate solution, one with a copper plate and copper sulfate solution. The sulfate, copper sulfate and zinc sulfate serve as the electrolytes that they allow for the metal cations and the sulfate ion. So the sulfate is a new type of anion we haven't really seen before. It's a sulfur with 4 covalently bound oxygens, so that there's an overall net charge of 2-. But these solutions must be joined by a wire and a salt bridge to complete the circuit. The salt bridge will allow the transfer of ions. It's essentially could be simply a cloth soaked in sodium chloride solution, and it has to be dipped into both solutions. It's not enough to just have the wire attach the two plates. You have to complete the whole circuit. It has to have a way to go back. Now, when you complete this particular battery, this Danielle cell produces 1.1 volts and always produces 1.1 volts under standard conditions. Now, while this is a little bit more cumbersome than a normal battery, it still serves the exact same purpose. So what do we have? What's going on here? The zinc is undergoing a oxidative process where the zinc is losing its 2 electrons to form zinc 2+. The copper is undergoing a reductive process where its copper 2+ is gaining 2 electrons and forming copper solid. Now, as this happens, you're going to have a buildup of positive charge on the left beaker and a buildup of negative charge in the right beaker, because we're losing the positive charges on the right and we're gaining positive charges on the left. The salt bridge allows for a dissipation of this charge buildup that would essentially stop the reaction. That as we lose copper 2+, the sodium can flow into the copper solution. As we gain the zinc 2+, the chloride can flow into the zinc solution to negate that. And that allows the circuit to continue. But when this happens, the electrons flee through the zinc plate and through the voltmeter, which allows us to measure the voltage, and then goes into the copper plate where they can be combined. And so what will happen is the zinc will slowly dissolve into solution, and the copper plate will get a little bit bulkier, a little bit darker. And because copper solution is blue, it will slowly clarify to be a clear solution as the copper leaves the liquid and goes into a solid form. As I said, as we allow this to occur for a period of time, the zinc will slowly dissolve into its solution, and the copper will slowly darken as the solution clears. Now, we could try something new. Instead of putting zinc in zinc solution and copper solution, we can try to put copper in zinc solution and zinc in copper solution. And we'll see something very interesting. When we put zinc in copper solution, the zinc immediately starts to develop pits and starts to dissolve while forming small little granules of copper onto the surface, and the solution clears. But if I put the copper solid into a zinc solution, nothing happens. That it doesn't work the other way. Putting zinc into copper works, but putting copper into zinc solution does not. And so what is happening? Normally zinc isn't soluble in water, but zinc 2+ is. So how are we dissolving the zinc into water? Is that the zinc is losing 2 electrons to form an soluble ion. The blue copper solution is absorbing 2 electrons to form the insoluble copper solid. It's absorbing the 2 electrons lost by zinc. And so what's happening when we put the zinc into the copper solution, copper sulfate, is the metals are directly replacing each other. And so we see the reaction. This is an example of a redox reaction, a reaction that takes place with the transfer of 1 or more electrons from one chemical species to another. Now, when we separate this into 2 individual cells, as opposed to just putting the 2 metals together, it becomes an electrochemical reaction, which is a reaction that produces a flow of electrons from one location to another, or is caused by this flow. So a reaction could be caused by the flow of electrons, but either way, the idea is we're not allowing the 2 things to react directly together. So that Danielle cell is an electrochemical reaction. But all of these work based on redox reactions. So not all redox reactions cause electrochemical reaction, but all electrochemical reactions need to work based on the redox principle. What exactly does redox mean? Redox refers to reduction, which is the gain of electrons, and oxidation, which is the loss of electrons. Now, copper 2 plus is gaining 2 electrons. Its charge is being reduced. It's going from +2 to 0. Oxidation is the process of losing electrons. Zinc is going from 0 to zinc 2 plus as it loses its 2 electrons. Another way to understand oxidation is the gaining of oxygen. So if in the case of our alkaline batteries, the zinc in the presence of hydroxide is gaining oxygen to form zinc 2 plus and O2 minus. So zinc oxide in the presence of water. One convenient way to remember this is the mnemonic oil rig. Oxidation is loss, reduction is gain of electrons. Oil rig, so oxidation loss, reduction gain. Got to remember, when you lose an electron is negative. So when you lose an electron, you become more positive. Same way as gaining an electron, you're gaining a negative. So the charge will go down. Now, one thing to remember is that electrons don't just disappear. They must be lost from somewhere and they must go to somewhere. Just in the same way that acids always need a base, under the Bronsted-Lowry definition of an acid base, reduction always needs an oxidation because the electrons have to come from somewhere and they have to go from somewhere. So we can understand these in terms of oxidizing agents and reducing agents. An oxidizing agent is simply a chemical species that acquires electrons from somewhere else and thus causes the second species to be oxidized. So an oxidizing agent oxidizes something else. A reducing agent releases those electrons to something else and thus causes that element to be reduced. So reducing agent reduces something else. A reducing agent gets oxidized. An oxidizing agent gets reduced. All these need to be put together to make the redox reaction. But if we split each into the oxidation step and the reduction step, we can split these into essentially 2 half-cell reactions, each of the oxidation and reduction reactions that combine to form the total redox reaction. So copper 2 plus and 2 electrons goes to copper 0 is the reduction half cell, and zinc goes to zinc 2 plus and 2 electrons is the oxidation half cell. And if you added them together, you would get zinc 0 plus copper 2 plus goes to zinc 2 plus and copper 0, the full reaction. So we can keep them separate to better understand them, but they work better together. To understand a Danielle cell that always produces 1.1 volts, we need to understand first, what is a volt? The volt is essentially a unit of electrical potential. It is the force of the battery. It's the pressure that moves electrons from one point to another. Like if you're doing work on an object by pushing it, that's the force in the kinetic energy realm. Well, when you're applying force to do work in the electrical realm, you use voltage. It's the pressure that pushes the electrons from one point in the circuit to another. Now, this is named after Alessandro Volta, who made the first battery, the Volta pile, in 1800 using a silver and zinc discs repeated in a salt solution. And that pile, the voltage did not depend on the size or the shape of the discs, just that they were silver and zinc. You would eventually change it into copper and zinc, much like the Daniell cell. Another thing we need to understand in electrical circuit is the ampere or amp. It's similar to velocity for electron. It is the unit of electrical current, which is the rate of flow of electrons. If a velocity is like meters per second, how many meters you run or how many miles per hour, this is like how many coulombs, how many electrons can travel through per second. The current is a rate of electricity passing through the circuit, named after André Marie Ampère, who was a contemporary of Volta and did work with electricity as well. You need both high voltage and high amperes to actually do damage to the body. That you can suffer very high volts but low amps and still be fine, and you can suffer very low amps at very high amps at low voltage and still be relatively fine. You need both of the same. For example, like a battery typically has very low voltage, but it can have a high rate of ampage, and so most batteries don't hurt you. But if you get electrical shock, like someone, the actual static shock actually has incredibly high voltage, but it's not applied for a very long period of time. So static shock is less likely to do damage. Now, while the book talks about, a 12-volt car battery won't kill you, it's not really dangerous, that's not really true. That they always tell you, make sure you be very careful when you're putting on the when you're testing your car battery or jumping your car battery, because you can kill yourself. Yes, a 12-volt battery won't necessarily kill you. It could be shocking enough that you can't easily release the battery, but enough of a voltage applied at the right place can cause your lungs to seize up, can cause your heart to stop beating, can shock your brain. So don't connect your brain to a car battery. Don't be careful when you're grabbing a thing that you're not completing the circuit with your foot, so it's running through your body or running from hand to hand. When you grab a car battery, the electrical circuit is going to take the shortest path. And so as it runs through your hand, probably through your blood vessels, it's going to pass directly through your heart, thus causing it to seize up. So be careful when you grab the car battery that you don't complete the circuit with your other hand. So despite what the book says, a car battery can very well kill you. So when measuring the voltage of the Daniell cell, zinc is always oxidized and copper 2+ always reduced. That the zinc and copper 2+ reacted, but the copper and zinc 2+ did not. That is because there was a greater potential of electron flow from zinc to copper. The zinc was pushing its electrons towards copper, and it was very weak to push back. Much like a strong acid will make a weak base, same way a strong oxidizer is going to be very poor to reduce. So we can look at the reduction potential and the oxidation potential of the two reactants. The reduction potential is the voltage produced by or required for the addition of electrons to the atom or ion. So the potential to be reduced. And the oxidation potential is obviously the voltage produced by or required for the removal of electrons from the atom. The energy that it produces or requires to be oxidized. It's not easy to isolate any half reaction by itself, because remember, for every oxidation, you need a reduction. So we can't just measure anything by itself. So we had to create an acceptable standard that is accepted worldwide to compare this with. And that's where we took the standard of hydrogen being reduced to hydrogen gas, protons being reduced to hydrogen gas, and we've set that artificially at 0 volts. Everything measured against that either produced or required a voltage to make this work. And we measured that and got a reduction potential from that. And so the standard reduction potential is the value of the substance's reduction potential as compared to the reduction of hydrogen ions at 25 degrees. And all these numbers are tabulated. And from here, we can calculate how much voltage it takes to do this versus that. How much voltage does it take to go from here to here? As long as the temperature is the same, only positive voltages reactions will occur. Only ones where they have a net positive voltage. More positive means more potential, which means there's a greater driving force to acquire electrons. The larger standard reduction potential, the stronger the oxidizing agent. The smaller reduction potential, the stronger the reducing agent. So lithium does not like to be reduced. Does not like to be reduced. It likes to be oxidized. Fluorine does not like to be oxidized. It likes to be reduced. And so we can do this. Note, when you reverse the reaction direction, go from lithium plus to lithium salt, and flip that around from lithium salt to lithium plus, we would also flip the sign of the voltage. So reducing lithium requires 3.04 volts, but oxidizing lithium would produce a 3.04 volts. Very similar to acids and bases again. So with a large concentrated acid, it means we'd have less base present. So a large reduction potential means a low oxidation potential. And in the next minute, we're going to look at a couple examples of how you could actually calculate this using the tabulation. In a battery, the machine connects the circuit to make a spontaneous reaction occur and then draw off its voltage. Now, if a negative voltage occurs, that means energy is required to make this happen. How do we calculate the voltage given the said reduction potentials? Well, to calculate this, we're going to add the relative oxidation potential to the reduction potential to calculate the electronic voltage that would be produced or required. So let's look at a couple examples. Now, the idea here is that on the chart, if you use the chart, it gives us only the reduction potentials. So to calculate the oxidation potentials, we have to flip the sign. Looking at the Daniell cell, the reduction potential, we have copper 2 plus goes to copper solid, and we add 2 electrons. And the voltage for that is 0.34. The zinc was zinc 2 plus, 2 electrons goes to zinc solid. However, in the actual one, we had zinc solid goes to zinc 2 plus, 2 electrons. And so that'd be positive 0.76. We flip the sign because we flip the direction of the reaction. So when I add 0.76 to 0.34, we get 1.1 volts. 1.1 volts. Looking at our reactions we did in the in our starting example, we mixed zinc goes to zinc 2 plus, which would have to be plus 0.76 because it's the oxidation. And we had iodine plus 2 electrons goes to 2I minus. If we looked up on the chart, this would be positive 0.54. So if I add these two values together, we have 1.3 volts. 1.3 volts. Now the other reaction, we had ClO goes to Cl minus, two electrons. If we look that up, that's positive 0.84. Now, since we're going from I minus to I2, that's negative 0.54. So we add these two values together. We add these two values together and would get a voltage of 0.3. When we add these two values together, we get 0.3 volts. So it's negative 0.54 because the iodine is occurring in the opposite direction. One more example. When we mix iron and zinc, the galvanic corrosion, we're having iron 2 plus or iron 3 plus, which is negative 0.44 Fe. But we have zinc going to zinc 2 plus, which is positive 0.76. When I add these two together, my voltage is 0.32 volts. All of these are positive voltages, so they would all naturally occur. If I were to ever get a negative voltage, it would need energy to run. Now, when considering batteries, you need to consider both the energy and the rate of release, as well as the practicality and the safety of having the materials. You could get the greatest voltage by combining lithium and fluorine gas. However, this high voltage would be at a cost of incredibly dangerous because fluorine is highly reactive and highly caustic. So if that were to leak, it could be incredibly dangerous. We have to be able to store these guys. So oftentimes storing these guys as oxides is safer than storing them as ions. And it helps contain the molecules in one place. Storing them as solids will help things go. If you can't get the voltage you require right away, you can actually put these batteries in series that will add up the voltages together. So if I have two batteries at 1.5 volts and I put them back to back, it would provide us 3 volts to run a system. The book looks at the lead acid battery. That the lead acid battery is has a spongy lead anode and a lead oxide paste cathode. The anode is the part of a battery that provides the electrons through the external circuit, but the cathode is the one that receives the returning electrons. Think of the anode in a battery as the negative and the cathode as the positive. Electrons would be repelled from the negative and flow be attracted to the positive. So anode produces the electrons and the cathode absorbs the electrons. One way to remember is anode has oxidation. They both start with a vowel. The cathode has the reduction. They both start with a consonant. But so the reaction for a lead acid battery, the type that runs your car is one side, the lead mixes with sulfuric acid to form lead sulfate and two protons and produce two electrons. The lead oxide mixes with sulfuric acid to form and two protons and two electrons form lead sulfate and two waters. So the net overall reaction is lead plus lead oxide and sulfuric acid forms two lead sulfates and two waters at a generation of 2.04 volts. In your car battery, there's about 6 of these cells put back to back, and that would produce the about 12 volts you need to start your vehicle. Now, you just need these 12 volts to start the initial engine, and of course to run the electronics when your engine is off. However, the majority of the processes once the car is going is run by the alternator and the generator that can produce AC and DC voltage. We're not going to get into exactly what alternating current and direct current do, but one of the key things is the alternator can recharge your lead acid battery when it's not in use. That's how you can keep your battery for many, many years, is that it doesn't run out because you're constantly charging and discharging and charging it back up. So what you're doing is you're taking the lead sulfate and the water and turning it back into lead and lead oxide. The advantage of these guys, lead sulfate is a solid, and that the lead sulfate solid forms on the grid that keeps it in place and doesn't allow it to just fall to the bottom of the battery. And by keeping it in constant contact with the plate, it allows us to put the active material back where it needs to go. And so we can keep using this for many, many years, so long as you keep a few things in mind, and that you don't allow it to get fully discharged and you won't allow it to stay discharged for a long period of time. The battery can last for a very, very long period of time. While batteries can supply energy for us, we can put energy into a redox reaction to run these reactions in reverse. The main example of this is electrolysis, which is the decomposition of substances by means of electricity. It's coming from the electrolysis. The Greek lysis means to loosening. Essentially, to lyse something in biology is to split open the cell, split a bond. We're splitting something apart using electricity. Our friend William Nicholson built his own voltopile in 1800, and by passing a current through water, he was able to split hydrogen back. It was able to split the water back into its hydrogen and oxygen. Now, this is a convenient way to produce hydrogen gas. Unfortunately, it takes a lot of electricity to do this. It takes energy to do this, so it's not always practical. Another thing you can do is you can take sodium chloride in water and electrolyze this back into sodium hydroxide, which is lye, our caustic cleaning solution, hydrogen fuel, and chlorine gas, which is a disinfectant. Now, chlorine, this process requires a lot of electricity, so we need a cheap and plentiful source. So what is often done is, I think this is actually done over at Niagara Falls over New York, the New York-Canada border, where the falling water is used to generate the energy to create the electricity to split this up. So you can produce lye, which is used in cleaning, and chlorine gas, which is used in disinfectant. And they talk about, we can use this to cure typhoid. It's basically chlorine can be added to drinking water as well as swimming pools as a way of killing bacteria, killing all the germs in there. Small amount is all you need to disinfect, but producing chlorine and chloride is no easy task. And so this was often done if you can use the electricity. Another example, which is a great one, is aluminum. By taking aluminum oxide, you can split it back into aluminum and oxygen. What you may not realize is aluminum used to be one of the most expensive metals. Rich people such as Napoleon III used to have aluminum dining set to bring out for fancy dinner parties, that aluminum was more expensive than gold because gold could be found pure in ores, while aluminum can only be really found in aluminum oxide. So it was hard to get pure aluminum. In 1825, Germans and Danes were able to create a process to get aluminum from alum. In 1845, a French scientist managed to scale this up. But still, aluminum was so labor intensive to produce, it was more expensive than gold. It wasn't until in fact, in 1884, when we built the Washington Monument, it was capped with 6 pounds of aluminum, that 6-pound aluminum pyramid at the top, because that was the most extravagant metal we could think of at the time. So we're just putting that up there, that the shavings of that could pay the salaries of all the workers for like a year. So it was incredibly expensive. Of course, in 1886, Charles Martin Hall found a way to make aluminum cheaply. He found that running a current from homemade batteries through aluminum oxide produced pure aluminum. He would later go on to form Alcoa. At the time of his death, he was worth something like $650 million, adjusted for inflation. Over his lifetime, aluminum went from something like $550 a pound. 7 years after he founded Alcoa, it went to $18 a pound. And 50 years later, around the time of his death, it was down to about 25 cents a pound. That aluminum has become one of the most blasé of all metals, but only because of the genius of electrolysis and Charles Martin Hall. But the same process can be run to produce pure silicon. That we can run silicon chloride with hydrogen gas and run electrolysis through them and form pure silicon and hydrochloric acid gas. And the same process is how we copper plate an object, or even chrome plating. You dip the object you desire into a solution of the metal, you run electricity through for a certain period of time, and you produce a thin film of the copper or the chrome onto the surface. Now, there's one last type of redox reaction we need to talk about, and that's kind of the natural type, which is corrosion. Corrosion is the erosion and disintegration of a material resulting from a chemical reaction. Specifically, one of the most common types is rust, which is the corrosion of iron to form various reddish-brown oxides of the iron. But generally, any form of corrosion is X amount of the metal plus 1/2 of Y amount of oxygen forms some sort of metal oxide of MXOY. You could form FeO, Fe3O4, Fe2O3. Zinc, you can really only form zinc oxide, ZnO. But certain things like aluminum can form Al2O3, copper can form CuO and Cu2O. You can form various oxides depending on the oxidation state of the metals. But some of these oxides can accelerate further corrosion, or they can retard further corrosion depending on the nature of the oxide. Iron, the rust, will actually accelerate further corrosion because it is flaky and porous, and so allows the more moisture to absorb onto the surface and oxygen to mix in and bind, and thus rust breeds more rust. If you don't remove rust from a vehicle, it will cause further rusting until the whole vehicle is gone. Now, certain things like zinc oxide and aluminum oxide will form a thin yet protective coating on the surface, and oxygen can't get through, and thus it will prevent more aluminum oxide from forming. That you have a thin layer of aluminum oxide on the surface of aluminum, and the rest of the interior is just fine. And with that in mind, we look at galvanization. Galvanizing is a process that provides a protective zinc coating to metals. This is often done various different ways, but you can dip, as my image shows, we can clean the steel and dip it into molten zinc to coat the thing. You could spray molten zinc directly on the surface. You can electroplate zinc onto the surface. There's various different ways, but the idea is that the zinc will coat the iron and provide a protective shell so that the iron will not rust for many, many years. And even if the zinc coating is lost in certain places, you get certain holes. Maybe someone runs into the thing, maybe you damage it, whatever reason, zinc will still act as a sacrificial electrode to prevent the oxidation of the interior metal until all the zinc has rusted. All the zinc has fully corroded. In fact, on large underground tanks that are too hard to galvanize, and they often add either magnesium, aluminum, or zinc block to them as a sacrificial electrode to help reduce the corrosion, make them last for a longer time. However, we can still have one other type of corrosion, as a galvanic or bimetallic corrosion, which is a corrosion when you mix two metals together, two different metals, and with a thin layer of electrolyte. Like you accidentally mixed some iron oxide with zinc, the iron oxide is going to reduce, and the zinc oxide is going to oxidize. This is essentially what happens when you have metal fillings and you bite into aluminum foil and you get a shock. You're seeing a small amount of corrosion happening as the reaction happens in your mouth. That if you mix two of the wrong metals together, they can actually react with each other. But that's not as big of an issue. So one of the big themes of this textbook is that the use of energy, or the use of energy. How did we use energy as a food? How did we use energy as a fuel? How does energy work? Now, the original gasoline four-stroke engine was built in 1876. And in 1900, most of the cars were actually steam or battery powered, with just a small fraction being gasoline powered. But by 1917, just a mere 17 years later, 98% of the cars were gas powered. That the majority of the vehicles, the steam and battery powered, have fallen out of favor. Now, while we still use electrical vehicles for special uses, for example, forklifts and golf carts are usually electric vehicles, something you can charge up. Electric vehicles are not incredibly common. Problems included at the time: low mileage, so you couldn't go very far; low speeds, you couldn't go very fast. The batteries had a very heavy weight and a very slow recharge time. In things like a forklift, that is not a problem. You actually want that weight to prevent the forklift from, tipping over. But in things like a car, the heavy weight is going to add to your mileage problem and your speed problems. Now, gas engines have improved, but they're still not fully zero emission, and they will never be zero emission unless we go to a hydrogen powered car, where when we burn that hydrogen, it produces only water vapor. But until we get to that, battery powered is the easiest way to go to get zero emissions. Now, when this textbook was last updated in 2003, Tesla was just being founded. Elon Musk wouldn't even join Tesla until a year later. So Tesla was still kind of a twinkling in someone's eye. For this writing prompt, give 150 words. I want you to take a deep dive into how electric vehicles have improved since 2003. And so you can approach this from many different ways. Looking at Tesla specifically, you can look at other cars, but you're looking at how electric vehicles have improved. You can look at mileage, you can look at infrastructure, you can look at like recharge speeds, you can look at all sorts of aspects from this. And you then also answer the question, is this still practical to continue to build electric vehicles or electric infrastructure? As I said, you don't have to focus just on Tesla. The idea is that where have electric vehicles come since 2003? Because the way the book talks is like, oh yeah, electric is the way to go, but it's still not practical. Well, now we see, yeah, there's a lot of electric vehicles on the road now. Are these good? Where have we come? So we can say, here's where we were, here's where we are now. And is this good? Should we keep going this way? Got to remember, gasoline industry gets a lot of money from the government. So before you're like, well, we right now have to subsidize all of the vehicles with huge tax breaks. Well, that's because we also subsidize a lot of the like oil industry and a lot of the corn industry to make the ethanol. So if we stop subsidizing them and stop subsidizing the cars, things would maybe approach their proper cost. So that's our prompt.